Hello everyone, welcome on our virus bulletin presentation, a new open source hypervisor-level malware monitoring and extraction system, and today we are going to present its current state and some further challenges. My name is Michał Leszczyński, I work as an IT security engineer at CERT Poland and I do malware analysis tools and infrastructure development. And also from time to time I'm breaking or auditing or fixing web applications.
My name is Krzysztof Stopczański. Currently I'm working in one of Polish financial institutions, but I'm going to present my research that I've done together with Michał when I was working in CERT Poland last year. I like breaking computers, and from time to time in my free time I like playing capture the flag competitions with P4 team.
So let's start from scratch. By analyzing ordinary consumer targeting malware, we could easily spot that we have many different samples packed by many different packers, but very often it's the same malware core underneath them. So we want to extract the malware core out of the packed samples to have easy identification and easy data extraction. And this is how we do malware processing at CERT.PL, essentially. We are focused on the malware unpacking and extraction of all the interesting stuff that is contained in the binary itself. So we take a portable executables, we put them on the sandbox, then the sandbox is making memory dumps out of the execution, and then these memory dumps are further analyzed by other systems. And this is how it could look like for some emotet packed sample. So we took a sample which I believe was sent through the email or distributed in other similar way. Then it arrived to our sandbox, it was unpacked automatically, and then our post-processing systems identified from the memory dump that this is the code of the family emotet, and moreover we've extracted all the information that was hard-coded within the sample, so the public key for encryption and all the hard-coded CNCs, all the information like that. So yeah, while the portable executable and the JSON are well-known concepts, and what about memory dumps? So the memory dumps, as far as we understand them, are the logical dump of the memory at given point of time, and they are relevant together with important metadata, which is the base address at which the dump was made. And also the reason of the dump is very important to know. Like, for instance, we did a memory dump because malware called some crypto API or internet API, which would indicate that this malware is already unpacked in memory. And the profit is the unpacked malware, or at least sometimes. So in order to have good memory dumps, we need good heuristics, and to have good heuristics, we need good behavioral monitoring. So why can't we just use an ordinary sandbox? So yeah, we use it, but there are lots of problems around it. So let's talk about problems we may encounter during the process of malware monitoring using conventional sandbox. So let's take this trickbot sample as an example. Trickbot is a well-known Trojan or stealer, which is distributed in a form of packed binaries for Windows, and this particular sample is using process hollowing using direct system calls. So since it's making the system calls directly, as visible on the listing shown on the slide, it's not possible for the user mode level sandbox to even detect such an activity. Another example could be this remcos sample, which is a remote access Trojan, and again it's targeting Windows consumers, and this particular sample is hollowing the service host using write process memory WinAPI call. So let's inspect the Cuckoo's hooking mechanism as an example. So this is how Cuckoo would place the hook on WinAPI, including write process memory. So basically, it would take the first 5 bytes of the function about to be hooked, and then it will override the first byte with the unconditional jump opcode and the next 4 bytes with the relative address of the hooking runtime. So now let's see some part of the remcos, which is binary matching the first export. This is the frame shown in the debugger, and then it has a loop which for each export finds the third instruction and then overrides the first instruction, and it overrides exactly the first 5 bytes to ensure that the function is unhooked. So it basically, this code basically reverts all the job that was done by Cuckoo previously. The sample was manually unpacked by Nazyvam. Thank you very much. So yeah, basically to counter that, Cuckoo could implement anti-unhooking and then could implement anti-unhooking. So then the Cuckoo could implement the further iterations of anti-unhooking, but usually the malware will be one step further always. So let's take Kronos as a third example. So this Kronos sample is a banking malware, which is again distributed in a form of Windows binaries and is making some strange kind of API hammering technique. So it is executing pretty long sequence of operations which are touching the registry keys, creating directories, and doing some other stuff. So on the slide we see an example of API hammering that some particular registry key was created over 40,000 times without any specific purpose other than just confusing the sandboxes which monitor all the activity like that. And after uploading this sample to Cuckoo's CERT.PL, we saw that the sample was reported, so the analysis completed successfully, but actually after clicking on the analysis it displays that the specified analysis does not exist, which would indicate that something crashed in between while analyzing this sample. And on our old and rusty Cuckoo one we saw that the analysis has failed because an existing connection was forcibly closed by remote host, which I believe was the case of the agent inside the VM just disconnected during the analysis. We still don't know the exact reason why, but this API hammering was actually successful. Okay, so let's do it on our own. So while choosing some other malware monitoring system, we could basically choose between user mode, kernel mode, being a rootkit inside the VM, or the external monitoring on the level of hypervisor. We have these 3 possible modes of operation, and we would not choose user mode again due to the problems that were already mentioned. So we have the choice between kernel mode and the hypervisor. While both are hard, we've established that the hypervisor approach would probably bring us much more profit in the long term. So let's go with the hypervisor. So in order to build the hypervisor-level memory dumping system, we need something open source to extend it. We would not want to write all this thing from scratch. And it must be a pretty decent malware monitor already. As we said before, we need to have a good behavioral logs. And we will just simply add the memory dumping thing to this project. And it turned out that the ideal project to perform such modifications is already present, and it's called DRAKVUF, which is a black box hypervisor level malware monitoring system based on the virtual machine introspection technique.
So what is VMI, virtual machine introspection? Basically, it's a system that is based on virtual machine's physical memory that analyzes it, makes translation, and can extract data from it, like, as we can see in this example, process list, virtual memory of processes, and so on. DRAKVUF. It's a system built on top of libVMI, and the shortest description might be strace for virtual machines. So it's a program running clearly on host, and by examining virtual machine's physical memory, it can show all the syscalls that are being executed inside the VM, the clear VM without any agent inside it. So what's next? We have DRAKVUF, that is a system for tracing execution inside Windows on kernel level, so we can trace syscalls, and it's stealth, so the applications cannot see the hooks inside, and it's pretty much undetectable. What we want to achieve is memory dump for extraction, for extracting malware core, and behavioral analysis. So we want to extract the information about Usermode API calls that has been called.
Let's talk about memory dumps specifically. So, as it was said, we need to dump interesting memory regions at interesting points of runtime. And to do it, we could use the existing libVMI features like memory inspection at low level, so we could read, write, or interpret guest kernel structures, and we could also place hooks on system calls in a way it is not visible to the guest VM, and we could even do a little bit more. So let's talk about our first very simple heuristic for unpacking. We could hook anti-protect virtual memory system call in order to check whether the memory about to be protected contains the MZ string as the first 2 bytes, and also whether the system call is related to the self process, so the process handle is equal not 0, the negated 0. In such a case, we could suspect that this portion of memory could contain the portable executable because of this characteristic MZ magic string at the beginning, and we could just dump this memory as suspicious. Another case could be hooking anti-free virtual memory. So in this case, again, we could check whether this operation occurs within the same process, and we could check the page tables of this process related to the address to be freed in order to check whether this page table entry is valid and flagged as writable and executable at the same time. In such case, we have the memory which is both writable and executable. We could dump it as an interesting RWX memory, which probably contains some unpacked malware. And here we have some problems related to the memory dumping this way. So for instance, if we have a single suspicious pointer, how we could find the corresponding memory region? So from what address should we start and till what address should we dump the memory? And the answer is to look inside the virtual address descriptors. So in the Windows kernel, for each process there is a structure called virtual address descriptor tree, which contains the information about all the allocations that were done by this process, so the ranges of the virtual addresses that are valid for this process, and also some information if some memory allocation is backed by some file, is it private or is it a shared allocation, and for instance, it allows us to determine whether this belongs to some DLL or some executable. So yeah, what if we don't have any pointer provided as an argument? So for instance, if we want to create a heuristic based on the anti-terminate process, it's not a memory related system call. We don't have any memory related pointer passed as an argument to this system call, but it's still interesting to inspect who called the anti-terminate process system call, and the answer here is to simply perform the stack walk. So how to perform the stack walk? Knowing the CPU context inside the syscall, because we are breaking the process inside the syscall. So we need to find where is the userland part of the stack, which is the value of the RSP on the userland. So what value would be restored when we are back in the user mode. And for 64-bit, the situation is pretty straightforward because we have k-thread structure in which we have a trap frame containing the RSP value. And if we are running the 32-bit sample on the Windows, which is 64-bit, then we have to deal with such strange thing as Windows on Windows, and we have to inspect the Windows on Windows context structure, which is actually hidden inside TLS slots in threat environment block, and it's not really well documented. So since we know where is the userland part of the stack, we have to unwind the stack in order to know what functions were on this stack. And we were researching many different methods to establish how to unwind stack reliably in a way that would work for both x86 and x64. And actually it turned out that the best method is just to go through the stack and take everything which looks like a pointer, check if it points to the valid range of the memory, and if it points to the executable page, and simply treat it as a stack entry.
About user mode hooking. First thing to mention is how DRAKVUF works. It uses EPT, extended page table mechanism in Intel processors, to transparently map guest memory to host memory. And it has some additional features, like additional privileges on this memory. And when we add breakpoint on some memory page, it gets cloned. We have, as you can see, the original page, the green one, and the copy with breakpoint. And by default, it points to this only executable red page. And when the process tries to read something from it, we have exception because there is no read privilege, and it gets switched to the original one, which doesn't have this breakpoint. It's single-stepped only for this read or write instruction, and then changed back to this execute only, which makes our breakpoint undetectable and constant, because if someone wants to write on them, they will be placed back. So why do we want to have user mode hooks when we have the better system calls hooks? Basically, we are analyzing user mode malware, so it's closer to us to have hooks on user mode calls. And sometimes it's possible to extract some information from system calls on what user mode calls were called on some sequences or some side channel read or writes, but it's not clear. It's a hacky way, so we wanted to make it clear approach. And two most important factors are that there are some user mode calls, for example in crypto API, that do not call any system calls. And last but not least, we can have full behavioral analysis, so list of all user mode calls that were called, which is helpful for analytic that might not understand everything from a list of clear system calls. And a short demo. We have a short application that generates random sequence using crypto API. As you can see, some random sequence. It's clear virtual machine with no agent inside. And from hypervisor level, we're starting some specific version of DRAKVUF, and see it now it's a little bit less random. So nice trick. It might be helpful to understand what are our possibilities. Okay, let's start. We need to find a place where the DLLs are loaded. Unfortunately, we don't have syscall load DLL. The closest matches are these two syscalls correspondingly to 64 and 32-bit applications. Every time the DLL is loaded, one of those two syscalls is called. And in this point, we know that DLL is loaded, but in a lazy way, it's not mapped to physical memory yet. DRAKVUF, unfortunately, can only operate on physical memory, so we can't just place hook on virtual memory. We need to make sure we had a page fault and the physical memory was populated. So we had several approaches to solving this problem. First one was to hook writes to page table, see if the write was to the memory that interests us, so that it's been populated, and if so, place the hook in this place. And this approach worked pretty well, but the code is complicated because of 4-level page table in Windows, and it was very slow because page faults happen very often in real life. Second approach was to manually inject page fault by placing some code that makes a read from interesting memory place, make a single step on it, then recover the state of processor that we saved before calling this instruction, and continue execution. And this approach was very fast, but unfortunately unstable, invasive. I think it would be easy to detect by malware, and hard to implement in DRAKVUF because it uses single steps itself, so it was hard to make a single step. And what was our third approach? It wasn't actually ours. We just saw that somebody made a commit to libvmi and made it for us, so that we could easily place page faults in hypervisor-level. And it was stable, fast, somebody did it for us, perfect. We lost like two months of work and the problem solved itself. Okay, so we're inside the syscall that loads our DLL. We parse the PE, the header, read the export directory. If it's not accessible, we put a page fault on it. Then we try to place a hook on function. If it's not accessible either, we put a page fault on it and finally put our hook. Some problems. The export directory might be corrupted, and placing a page fault on it would then crash the system as a whole. But we can hook handler for blue screens in Windows and pretend nothing happened. So before placing the page fault, we put a flag that we're messing with something, and in this handler we're checking if it's our fault, and if so, we're just silently continuing execution. If it's not our fault, we just pass the execution and show the blue screen. Another problem. Remember the remcos malware that took down the hooks? In this case, it would not be taken down, but in Windows we have a copy on write mechanism. So the DLLs are shared between processes, and if some process wants to make a write on its own DLL, the shared page, physical page, is copied to another place, and unfortunately we will lose our hook. So we can hook function that is responsible for copy on write and see if the page that is currently copied contains some hooks, and if so, place the hooks on the new page. And the best test program for us was Internet Explorer, that does almost everything that is allowed in Windows, including writing on its own DLLs. So on the top you can see the message box function from user32 DLL, and on the bottom you can see the same function in Internet Explorer execution. As you can see, it passes the execution to its own code, and on the left you can see the original code, and on the right the hooked code by Internet Explorer. So it behaves just like malware. And here's the list of DLLs hooked by Internet Explorer. We didn't know why it tries to do this, why Internet Explorer behaves like malware. Now I can say it's shim mechanism that is used for compatibility. So Internet Explorer has its own better APIs.
So right now, let's use our user mode hooking features in some funny and, I hope, illustrative way. We have clean Windows 7 VM with Heroes of Might and Magic 3 installed in it, and it is monitored by DRAKVUF. And we could see that DRAKVUF could detect, in this case, how much money we currently have in Heroes of Might and Magic 3. So yeah, we could see that we are gaining additional money by passing the turn, which is a normal thing in Heroes of Might and Magic 3. And we also can set the amount of money we would like to have at the moment using the volume bar of the Windows Explorer. So that's basically detected by our external monitoring program, and then the memory of Heroes 3 is altered. So after solving all the problems previously mentioned, we've created another project called DRAKVUF Sandbox, which is basically a wrapper for DRAKVUF containing a web interface, an easy installation process, sample queue, and all the remaining basic features you would expect from a simple sandbox. Here is the screenshot from one of the early versions of the DRAKVUF sandbox, which displays the WinAPI logs of some process in a web interface. It's free and fully open source, so we encourage to visit us on GitHub and to try to play with a DRAKVUF sandbox, and any feedback would be appreciated. We are also constantly researching whether we could use additional hardware features to enhance our existing malware monitoring process, and one of the examples is Intel processor trace. So there was an attempt to implement the IPT feature support within the Zen hypervisor, but the patches were unfortunately abandoned. So basically we took them after a few years and we fixed them and resubmitted them as a new patch series called Implement Support for External IPT Monitoring. This is the path of our further research, and more details will be coming soon. So to summarize, I would like to highly encourage you to try all the open source projects we were contributing into while making the described solution, and I would also like to say thank you to the CERT.PL reverse engineers, Nazywam, Pesrock1 and MSM, for important remarks and hints about malware monitoring. Also, special thanks for Bonus, Chivai and Konstanty, which are CERT.PL developers, for helping us with the further development of DRAKVUF and DRAKVUF Sandbox. Moreover, I would like to say thank you to Maciej Kotowicz for providing many good heuristics for memory dumping and some hints about using them, and to Tamas Lengiel for the fact he is a creator and maintainer of the DRAKVUF project on GitHub, and many times he provided a lot of helpful remarks during our research. If you would like to access the data we've shown on the emotet examples, so our malware data, the data about the static configurations of the malware, you could apply at MWDB CERT.PL. We have the free service within which we share a lot of data about malware with white hat external researchers. And at this point, I would like to thank you for your attention.